Thanks for joining us. My name is Karen Corman, and I have the privilege of being the Executive Director of the UIC Alumni Association. Welcome to the UIC Alumni Exchange Series. Through the UIC Alumni Exchange Series, we work to bring our alumni and friends a variety of programs and topics so you can explore, connect, and even escape from the everyday with a community of UIC alumni, faculty, and staff experts. You'll hear me say this a few times today, but I encourage you to visit go.uic.edu/alumni exchange for the latest and greatest programming. And with that, I'm very excited to get our program started today as we are joined by UIC faculty member in the College of Liberal Arts and Sciences, Associate Professor Max Berkelhammer. Although it may be hard to tell from the weather this morning and the last few days in Chicago, Dr. Berkelhammer believes that we might be facing the warmest winter in the last million years. He will discuss his research and how we know we are experiencing changes compared to the past. We are excited that he's here today to talk to us about the saga of climate change. Thank you so much, Dr. Berkelhammer, for being with us, and I'll turn it over to you to begin the program.
Thanks so much. I appreciate the introduction, and thanks everyone for coming. This is a really nice and fun honor for me to get the opportunity to speak with you. I was when I was prepping for the talk this morning, I was thinking about this project I had been working on a few years ago, which was thinking about drought in California. And I was invited to give a talk out there. It was in San Francisco. I flew out the morning of the talk. I got up and it was just this torrential downpour. So I'm sitting there giving this talk about drought, looking out the window at this rain pouring down, and I couldn't help but think about this morning and the irony of speaking about the concerns about warming and these absolutely frigid temperatures. So with that, I'll jump in. So I'm a professor in the Department of Earth and Environmental Sciences. I run a group here called the Atmosphere, Climate, and Ecosystems Lab, where we look at the interactions between the atmosphere and Earth's climate system and land surface processes and ecosystems. Here are a couple of my students, Will and Kyle, taking part in one of our projects in Colorado right now, looking at climate change and in the forest, alpine forests in that area. So I've been at UIC for 8 years and had just wonderful experiences with my students and faculty here. So it's a really nice chance to speak to some of the alumni. When I was asked to give this talk, I was reminded of this headline, maybe some of you saw over the summer, is from the New York Times. Is this the coldest summer of the rest of our lives? And this was it's kind of intended to be a sort of a provocative headline, thinking about us in the midst of climate change, and that each summer that we will experience will likely be warmer than the summer that preceded it. And although it comes across as kind of provocative, if you look at temperature records over the recent historical period, this is global temperature changes back to 1850. And if you're like myself, younger than 70 years old, if you're born after 1950, it's actually true that most summers you've experienced thus far have been, in fact, the warmest of your life. So you're already in the midst of this change. Although it might feel subtle and nuanced, you might not feel that each summer is the warmest. In fact, that is what you have been experiencing. And so it's not hard to project forward and think about how this trend is going to continue. And in fact, each of those summers you'll likely experience moving forward are going to be the warmest. It's tough to say exactly what that will feel like, but one way that researchers have tried to convey this information is thinking about where we are now and how that might feel in the future. So this is a plot showing Illinois, what Illinois temperatures feel like moving forward in time. And so one projection is that by the year 2080, so not really that far away, the summers in Illinois will feel a bit like summers in Texas might feel today. So that to give you a little bit of a sense of what that might actually feel like for you. However, as an earth scientist, as a climate scientist, While we know with a fair degree of certainty that climate is warming and changing, and these summers and winters are getting warmer, there's a lot of uncertainty in these projections. And one of our goals is trying to get a better handle on what that uncertainty is. So this is another set of projections. So I won't show too many graphs, but I am going to show a few up front. So this is temperature change on the vertical axis and the y-axis. This is time on the x-axis, moving way forward into the future, into great-great-grandchild land. And you'll see that the future has a remarkable range of possibilities, ranging from conditions that might be 12 degrees warmer than today, so just an absolutely unrecognizable global climate, versus the conditions that might be pretty similar to today. And you'll notice too that there are these three different color lines, or these three different types of scenarios. And one is, this red line is what we call the business as usual scenario. That's that we continue along the current trajectory in terms of our fossil fuel use and land use change. Second is the case where by 2040, so 20 years from now, we start to decline fossil fuel use, and then the purple is the case where we've already stopped. We've already started to decline our fossil fuel use. We know, of course, that's not, unfortunately, the scenario we're on. So these three lines capture the uncertainty in human behavior, the choices we make in terms of policies, in terms of economics, things like, will new energy technologies make greenhouse gases obsolete? What choices will the government make in terms of subsidizing certain energy use and other things? This is not what I think about a lot. I don't think a lot about human decision making in my research. What I tend to think about is the other source of uncertainty, which is that even if we knew the trajectory of in terms of the economic and policy decisions moving forward, there's still this massive cloud of uncertainty associated with the climate system itself. How will the climate system respond to increases in CO2 or methane or other ways that we perturb the climate system? And there is, even within the climate system itself, even if we knew the human choices of economic and policymakers moving forward, there's still a remarkable amount of uncertainty in the climate system itself. So you might ask the question, why is the climate's future so uncertain? And I'll give this example. This is just one example that might help to illustrate this point. This is a photo I took a few years ago. This is looking at the receding edge of the Greenland ice sheet. And so I was in a project, we would come back to Greenland every summer and document certain elements of the changing climate there. And each year, this edge of the ice sheet moved further and further back from this hill slope that I was taking the picture from. And what happens is that as that ice edge recedes, two things happen. One is you take a very light colored surface, which is ice that reflects sunlight and has the effect of cooling the climate, and you replace it with this darker surface that absorbs light and warms the surface. It also starts to become populated with plants that, as they grow and photosynthesize, absorb CO2. So on the one hand, you're replacing this light colored surface with something dark. So that has the effect of actually warming the climate more. On the other hand, you are adding new plants and new photosynthesizers and decreasing CO2 from the atmosphere, which has the effect of, in fact, cooling the climate, or at least slowing down the rate of warming. So if you take this very simple example of the ice sheet receding, it's actually triggering two responses. One, where you're going to speed up the rate of warming, and the other, where you're going to slow down the rate of warming. And the truth is, we don't necessarily know how these two are going to compete with each other. So as climate scientists, we often argue or discuss about whether the climate system, something as complex as the climate system, is resilient to change. And what I mean by that is, as you move the system, as you perturb the system with higher CO2 or other things, will it resist changing and in fact kind of self-stabilize itself and be, as I'm writing here, resilient to change? On the other hand, you might argue that as you start to perturb something as complex as the climate system, it could turn out to be very sensitive, where a small change actually snowballs and generates a massive reorganization in the climate system itself. And so when you look back at these projections of the future, when you think there's this extreme 12-degree warming versus a more modest scenario, what these represent is the difference between a climate system that is fairly resilient. So as it gets changed, it self-stabilizes versus a climate system that's extremely sensitive, that as we perturb it through different human activities, it starts to fall down the slope and starts to snowball into a very different climate system. So one of the ways earth scientists try to understand the sensitivity of the climate system to change is to develop a historical perspective and look back through Earth's history to try to get a handle on how sensitive our climate system is to change. We know, for example, as you go back in time, that there were periods where the Arctic was covered with, lush, wet forests. So the Earth was extremely warm. And there were other times where the Earth was actually covered pole to pole with glaciers. So we know the Earth's climate that we're experiencing today is not necessarily, does not represent the full range of the climate system. It can in fact, has in fact experienced very extreme changes over history. And so the challenge is that we've only measured the temperature on Earth really with some degree of certainty for about 100 years, which is just not nearly enough time to develop a handle on how sensitive the climate system is to change. We know as CO2 rises, the system is warming, but we don't know if that's going to spin out into a really extreme warm scenario or if there's going to be some self-stabilizing features in the system. And so Earth scientists rely on different types of natural archives, we call them proxies, to understand that range of behavior of the Earth's climate system. And from here on out, I'm going to talk a little bit how we develop these records and how critical they are to us getting a better sense of what the future of the climate system might look like for us. So I'm calling this, I call the talk the Saga of climate change. And the reason I'm calling it that is I'm now presenting to you an example, and I'm going to show you how this example was actually generated. But this is a look at climate, the temperatures of Antarctica over about 1 million years. And when you look back at the climate changes over this period, you see that it's undergone massive reorganizations. It's had warm periods and then collapsed into cold periods, and it's oscillated between the two, and often in these really abrupt ways. And these historical changes in climate have forced migrations or collapses of civilizations. They've generated extinctions of animal groups. They've made landscapes completely unrecognizable, bury them under ice, or flooding them with rising sea levels. So that saga for me is that historical perspective of this very dynamic, changing climate system that we live in. So moving forward, how do we reconstruct the climate? I showed you this chart of almost 1 million years of climate from Antarctica. Obviously, we haven't been measuring temperature that long. So how do I know what the temperature history has been like in Antarctica and the globe? And the example I'm going to use is if we start with this trash can here. And the very bottom of the trash can in your house has your oldest trash, and the top has your youngest trash. And if for some odd reason you decided, I don't want to take out the trash for a year, and you just kept jamming it in deeper and deeper, you'd start to develop a record, a climate record actually, in your trash can. And so you could start to sort through that record, that trash can, and start to find evidence of what the temperature was like over that past year. You might see different things that were indicative of warm weather or things that were indicative of colder weather. And fundamentally, that's when we reconstruct climate, that's what we're doing. We're looking back through places on Earth where trash or other things are accumulating and use them to develop quantitative historical records on the climate system. So you could imagine, for example, and if you take a moment to think about this, if you didn't take out your trash for 140 years and you let it just accumulate there, we know 140 years ago it was about 1 degree or 1.5 degrees colder. So what clues might you find in your trash that the temperature was colder back then? And so I'll just leave that as kind of an open question for you to think about what evidence you might find in your trash for a colder climate. But Where we look is not actually in trash cans. We try to go deeper and we go onto the ice sheets of Antarctica and Greenland, and we dig into those records to try to find what the temperature used to be like. So I'm offering a little bit of a warning here that if you already feel a little bit cold, these images are going to make you feel, are already making me feel a lot colder. So glaciers build up for thousands or millions of years, and they develop into these layers of ice, and you can probe those layers of ice to develop these historical perspectives on climate. So here I am trying to get some old ice. This is not a very effective way to get deep into the ice sheet, it turns out. There are other ways. So here's an example of what this looks like. This is about 30 years of ice, so not particularly a particularly long record, but it illustrates here these layers. And you can look at these layers and you can look at chemical signatures in these layers to try to figure out what the temperature was at these various periods of Earth's history. Like I said, 30 years doesn't give us a lot of perspective because we knew what the climate was like 30 years ago. But it turns out if you get to the bottom of the Greenland ice sheet, you can find ice that's 150,000 years old. That's pretty useful because we don't have a lot of information about what the climate was like 150,000 years ago. If you make it to Antarctica, you can find ice that's 2 million years old. So that gives us a really long historical perspective on our climate system. So how do we do this? I'm going to get into a little bit of a field trip mode here, how this actually works. When we travel, this is work that was done in the Greenland ice sheet. We work with the Air National Guard to get transit up to the top of the ice sheet. So here's our plane landing. Here's the guy checking us in for our flight home here from the top of the ice sheet. We work at a camp. There's quite a bit of infrastructure that's needed to develop these kind of records. So it can't just be done in isolations. We need various support staff. And so this is what's called Summit Camp, which is on the top of the Greenland ice sheet. And it includes places we sleep. The scientists sleep in these tents embedded in the ice sheet. And it's part of what we call Tent City, which is a network of where the scientists sleep on the camp. Here's an example showing something called a fog bow that forms over the ice sheet. This is when it's like a rainbow, but when instead of water in the sky, you have ice crystals in the sky. There are places to take care of the big house, where you eat, where you do your laundry, where your kind of living space is, a TV, a hot shower even. And then there's a greenhouse. This is where the staff live that support us in the scientific endeavors we're taking part in. There's a garage. This is pretty critical to maintain bulldozers and other vehicles, because in order to get the planes in and out, we need to maintain a runway. So here's an example of the garage here where that equipment is maintained. This is also happens to be a 4th of July celebration. We were up there on 4th of July. We were doing a tug of war. But at the end, the infrastructure and support is really about the science here. And so part of the science which I take part of is developing, using the ice sheet to develop historical pictures on climate change. But there's also groups, for example, who have radar, who are looking at the atmosphere over the ice sheets. And this is called the Swiss Tower, developed by a Swiss scientist, where we measure directly the climate over the ice sheet. So our research group at the time, we had a lab under the ice. Here I am descending into this lab that was at the base of the tower. This is our base of operations, where we were making the measurements in the ice sheet to try to develop this historical perspective that I've been trying to convince you I was critical for understanding the sensitivity of the climate system. Here we are installing some equipment within the ice that continuously measures the conditions on the ice itself. And we can tie those measurements at the surface to try to help understand the temperature signal that's embedded within these layers of ice that I showed earlier. Now, in order to get really deep, miles deep in some cases, you can't just dig a hole. You need to use an ice core. So I like to think about these ice cores as time machines, because as we get deeper and deeper, we're gaining access to ice from older and older periods of time. So this is an image on the top left showing an ice core that is used to cut through the ice, and then this would be a borehole that we dig. Unlike let's say if you were an ice fisherman or something where you just wanted to dig a hole through the ice, we don't just want to dig the hole, we need to capture the ice that's coming out. So we use these coring devices that are specially designed to both cut through the ice, but also capture the ice so we can bring it up to the surface and make measurements on it. When we're ready to do that, we pick a site to drill these sites from. So here's one of our sites from the 2013 field season. We have a small tent, which was our base of operations, our snowmobiles where we get access to the site. Here's some images of us establishing the drill camp and starting to drill, myself and my colleague Hans Christian Steen Larsen from the Netherlands. Here we are digging the core and transporting it back to the little tent where we were processing the samples. Here's our borehole, getting deeper and deeper progressively over time. As I mentioned, we have these specialized cutters that are used to cut through the ice, and then these little teeth that catch the ice so we can bring them back to the surface. We were fortunate in that season to also have some visitors, some Greenlandic students visiting who helped out with some of the drilling. I have to admit, having a break from drilling was certainly a welcome opportunity for everyone involved. So at the end, what we're doing is progressively pulling out deeper and deeper sticks of ice, as shown here, an example of one of these sticks. And they come out in generally 1 to 2 meter sections at a time. And if you want to go back 125,000 years, which was the goal of the projects in Greenland, you have to go really deep. In fact, if you picture the Willis Tower here, in order to get to the bottom of the Greenland ice sheet, you need to dig about 6 Willis Towers worth of ice out of the Greenland ice sheet. So these are remarkably deep holes that need to be dug. When you're all done, you're left with this amazing collection, miles long collection of ice spheres that get stored in an ice core library that are actually accessible for other researchers to use as well, so they can take advantage of the efforts of digging these holes. So each of these layers of ice represents a moment in time, and so you can slice the ice into narrow slices, melt them down as we're doing here, storing them in small vials, carefully labeled, pack them up, ship them back to Chicago, and one by one, we make measurements on each of those layers of ice. This is my lab at UIC. These are a couple of my undergrads. They have now long since graduated. This is a little bit of a dated picture, but we make measurements on each of those layers of ice to try to develop these long records of climate that I've been discussing so far. So I'll start to kind of conclude this a little by saying I started this talk thinking about the future, which is these projections of how things are expected to change, this idea that each summer we're experiencing is likely going to be, the next one is going to be warmer than that. Then I'll say to really understand what the system is doing, we need to look into the past. We need to drill down into the ice. We need to make these measurements to build this long perspective on Earth's climate history. And now what we can do is patch these two things together. So on the left-hand side, this is a 2 million year record of Earth's temperature. And you can see, as I mentioned, the saga temperature going up and down over the last 2 million years. And then you see these little colored lines at the very edge. And these are the future. So now what you can see is, yes, the climate has always exhibited, or at least in the last few million years, this kind of sensitivity. It's oscillated, it's highly dynamic, but the future that we're looking at is very much unprecedented in the context of the last 2 million years. And so indeed, each winter might be the warmest winter in the last million years, as I developed as the premise for this presentation. So I'll kind of conclude by saying the Earth's climate is extremely dynamic, and we know that from developing for this historical perspective. And for example, not that long ago, Chicago was under a mile of ice. Chicago would have looked very different 10, 12,000 years ago than it does today. On the other hand, we really don't have to go that back far in time when these ice sheets in Greenland and Antarctica had melted back and the sea level had risen, and Florida would simply have not been part of the map. So it's a very dynamic system, and history tells us that it's capable of experiencing significant amounts of change, even before humans were perturbing it to the extent we are today. So a lot of these future scenarios can seem really abstract. This idea of sea level rise, flooding areas out, massive wildfires, the melting of Greenland and Antarctic ice sheets. But when you view these scenarios through the lens of history, they become a lot more tangible and a lot more tractable. And so that's really, as earth scientists, a lot of what we're trying to do is get a handle on what the history, Earth's climate history, can teach us about the future. So I will conclude there. I realize there was a lot of information, but I really do appreciate your attention and all of you for coming and supporting the Alumni Exchange. And I would love to take any questions you might have.
Thank you, Dr. Berkelhammer. That's so interesting. And I have so many of my own questions, but I'm going to stick to, to what was submitted. I really actually want to start with just, how did you get interested in this?
Yeah, well, I was an earth science major as an undergrad, and I was I'm kind of old enough that climate change was a sort of developing problem at the time. It wasn't as discussed as it was today, but I remember reading about it and having a kind of very strong response to that and concerns about that, and I think that motivated a lot of my decision about going into this field.
So what do you hope that your research will achieve? Is there sort of an end crystal ball that you really hope at the end this is what it will do?
I mean, I think for the research I'm hoping to do, what I really hope it will do is continue to help us develop less uncertainty about what the future holds. So I think in most fields and most things we do, if we can reduce uncertainty, we can make sort of smarter decisions about how we manage our resource and decision making. So the type of things. So really, what I hope to do is by developing a better understanding of the climate system, having a more certain perspective on what the future holds.
So as you were talking, the question that kept coming to my mind, and I have a much better, well-written question. What I'm about to say was, what can I do? And so the question that came in is, can individual actions mitigate the rate of change, or do you think we need large-scale international coordination like the Paris Agreement, or both?
Yeah, I mean, I think it has to be both. I mean, I think there's a lot that can be done locally, a lot of individual decision making that can have big impacts that should be adopted in terms of like the type of energy that we're relying on and renewable, sustainable energy sources at the local and regional level, of course. But then I think also the reality is this is a cross-border issue, and that a lot of what I'm talking about is global change, and the fact this is a global problem, and while kind of local solutions will have a lot of impact, the discussions need to transcend that and be conducted at global levels.
Thank you. I was thinking when you were showing the example of trash that if my daughter was watching it, she'd say, well, I'm not going to take out the trash and let's just have our own experiment here. But I thought that was a really interesting way of presenting, just, thinking about how things become layers and what happens. Somebody had asked, what is your near future work? Do you plan on going back to the Arctic for more ice studies?
Nothing, nothing super exotic in the near term. I was fortunate to take part in pretty extensive program in Greenland and Antarctica. Though I have to admit, on a personal level, they are extremely disruptive to one's life. You give up your Chicago summer to spend it in absolutely freezing cold ice sheet, for example, not to mention, not seeing your family and friends. So I've moved along from that a little bit, but the work we're doing now is a little more regional. We've been thinking about actually some Midwest problems and thinking about how land use change and in switching from agriculture or switching from prairie to agriculture, and in some cases back, how that can be part of the process of mitigating climate change. And so we've been working on that. And then I've had this longstanding project, as I mentioned in the beginning, which is thinking about how warming in the western US mountains and changes in snow is affecting the forest systems there. And that's a project I hope to continue for the next few years.
Wonderful. I assume that this probably happens to you, but when you come across people that say climate warming, that's not really a thing, what do you say to them?
Well, I mean, I think for me, it has to be, you have to look at the data and you have to rely on the data. I think you have to come as a scientist with an objective perspective. I try not to be an advocate in the sense of coming with trying to prove something. I try to look at the data from the most objective standpoint that I believe I can. And so and the conclusions that I've drawn and the conclusions drawn by the vast majority of their scientists are based on the observations we have. And so and that's what we'll continue to do. If the observations start to show something different, for example, like the warming starts to decelerate or slow down, and that's what the climate, that's what the data is showing us, then we'll respond accordingly, and we'll develop new theories on climate to address that. But I think the only thing we have is the data, and in a sense that people are approaching this problem with a spirit of objectivity.
Yeah, thank you. Somebody had asked, once the average global temperature has reached a higher level than desired, can the average temperature be lowered through human interventions?
Yeah, definitely. I mean, there are ways that have been discussed and advocated for. I mean, I think the conservative approach is to think about what we're doing that's impacting the change and slowing that down. So things like reducing CO2 emissions. So that may not be intervening in the sense of changing the climate system, but it would be mitigating the things we're doing to that are causing the warming. But there are more extreme things that have been discussed, and some of those include, for example, after volcanic eruptions, there's dust that is shot up into the high levels of the atmosphere. And that dust generates a kind of a veil over the earth, and it reflects energy from coming in from the sun. So it has a cooling effect. And this is well documented. After large volcanic eruptions, the earth has a tendency to cool slightly. And so there have been proposals to take advantage of that dynamic and essentially launch these particulate matters into the upper atmosphere, reflect some of the sunlight coming in, and actively cool the climate system. So this is part of a broader class of engineering that's sometimes referred to as geoengineering, which we would take advantage of natural processes in the Earth system and use those processes to actively cool the climate system.
Interesting. Thank you. Would you, or could you briefly go over how fossil fuels affect the climate?
Sure. I mean, the main, so I'm going to momentarily put aside the public health issues, which is that burning of fossil fuels can have direct, immediate public health impacts. But from a warming perspective, primarily what happens is when you burn fossil fuels, you generate two of the byproducts are water vapor and carbon dioxide. Carbon dioxide, and you've certainly heard this term, I would presume, is what's called a greenhouse gas. And what a greenhouse gas is a gas that absorbs a type of radiation called infrared radiation. And infrared radiation is a type of radiation you can't see with your eyes, but it is emitted from all objects that that are above 0 degrees, absolute zero. And so when that infrared radiation is emitted from an object, if it interacts with a CO2 molecule, that CO2 molecule absorbs that energy and it heats up. And so as you add more CO2 to the atmosphere, the radiation being emitted from the Earth becomes absorbed and the atmosphere heats up. And so that's what happens.
Interesting, thank you. Is there any data on the long-term impact of reduced carbon emissions during the early stages of the pandemic, or were the reductions too brief to be significant?
Yeah, there have been people working on this in different ways. So I'll step back to another example, which is before the pandemic, during the Great Recession, when the economy slowed down, there was a reduction in CO2 emissions associated with that. So, and that was kind of a longer term impact. So we know there's a relationship between economic activity and greenhouse gas emissions. In terms of the pandemic, it's very regional, the impacts. So in some cases, like for example, reduced air traffic might have had impacts on air quality and CO2 emissions. On the other hand, like the trucking sector did not really decline during the pandemic. We were, as you know, moving products around as fast as we could, as efficiently as we could. And so there was a kind of a momentary blip in CO2 where CO2 declined right when there was some of these initial lockdowns, but for the most part, we've rebounded from that, and the impact has not had a lasting effect.
Yeah, I always thought it was interesting during the pandemic where you saw like the fox or whatever running down Michigan Avenue, and just the impact on the environment and the animals and just everything. How it was just, I think that could be probably a whole PhD study that could be done.
Yeah, no, and that's true. I think like for a lot of bird populations in the city and other things, they really benefited from the pandemic. From an emissions standpoint, it was a very temporary. It seems like it was a very temporary blip.
Yeah, no, thank you. It's really interesting, and I know I've heard different aspects. Then I've also heard about the rats and how that impacted the rats in the city. So you know. Another question came in. Some scientists are concerned that the temperature has risen in a shorter period of time than we had previously believed. What are your thoughts on this, and when do you estimate we'll hit 2 degrees?
Yeah, I mean, I think when we developed, and I talked about this a little at the beginning, these kind of scenarios where, like, if we choose one pathway in terms of our, let's say energy sources, fossil fuel use, we're going to follow one path. We call that the business as usual. Where if we follow other pathways, that the rate will be slower. I would say for the most part, we have, generally speaking, followed the business as usual pathway. And if you go back to even some of the early climate projections from like the 80s or 90s, we're not far off from what some of those original projections had been. So I think we're, generally speaking, warming at the rate we've kind of expected based on the decisions we've made. I would say. And as far as when we'll reach 2 degrees warming, I think there's a lot of uncertainty on that. I suspect it'll be by the end of this century. Seems highly probable, but there's still a lot of space we have for decision making that might slow down that rate. So I would hope we adopt those approaches.
Thank you. You shared the picture of your two student worker or your two graduate students that were working with you. And I know you said that was from a few years ago, but I assume you still have some students that are working with you. How do you feel your undergraduate students who will feel some of the greatest impacts of climate change feel about the research that they're doing with you?
Well, I'll say that was actually this summer. That was new. That was just a few months old. Well,
oh, my apologies. I thought you said it was a while ago.
No,
I love the pictures, by the way.
Yeah, no, but they go out every summer, different students. So, I think, I guess I try to separate some things here, which is in terms of the student involvement in the research. I mean, I really, and this goes back to trying not to be necessarily an advocate in my role as a climate scientist, which is I try to give the students, help them develop skills so they can, continue on in their careers or in graduate school. And from that, we try to kind of focus on the problem we're looking at and develop skills to achieve those goals, as opposed to sort of like, you're younger than me, you're going to be around for a while, you got to figure out this problem. I try not to kind of pass it off on them. So the experiences I try to pass on to my students are one of empowerment in terms of skill development and in experiences that are outside of the classroom and broaden their exposure to the Earth system. And so that said, I also know from conversations that students these days feel a lot of anxiety about the climate system and the changing climate. And I sympathize with what the level of anxiety that must feel like, how things are changing and things they've grown accustomed to may not be around as they get older. So
it's the old phrase of the more you know, the more that it can cause you anxiety, or the more, just you're asking more questions, which is exactly what education does. One alumnus shared that he talks to Illinois farmers, and one asked him about the CO2 cornfields that are what they're absorbing. He thought his farming might be better for the climate if his land was forested or prairie. Do you have any thoughts on that?
So prairies are really amazing, what we call sinks of carbon. And as prairies develop, carbon starts to accumulate in the soils below the prairie. So they're really rich with carbon. And so one of the strategies for slowing down climate is, in fact, advocating for things like prairie development, because over time, what prairies are doing is actually taking carbon out of the atmosphere and sticking it into the soils for long term. So it's essentially trapping atmospheric CO2 and letting it accumulate into the soils. So I think from a purely climate standpoint, there are a lot of benefits for shifting to prairie type ecosystems from a climate standpoint. That said, this is a complicated problem because we also need food. So we need affordable food sources. So I think, and local food sources. So I think, if we were to trade farms for prairies, that cannot be a universal solution. But I think taking advantages of what prairies can offer, using them in certain circumstances, or doing mixed cropping systems where we might have prairies interspersed with corn or soy. I think there's a lot of opportunities there for climate mitigation.
Thank you. You're right. It's important for many reasons. I'm going to apologize in advance because I'm not sure I'm going to pronounce this correctly. So the question is, how much are you concerned about the Wades Glacier? The THWS Am I saying it completely wrong?
Yeah. Yeah, no, that's good.
Well, sorry,
Yeah.
sorry, let me finish the actual question. So the glacier
Okay.
and recent evidence estimating it could potentially break up or dislodge within 5 years. Based on your experience, how real of a threat do you believe this is?
I think its breakup seems from, this is not something I know a lot about. So I don't want I don't want you to take what I say with too much gravity, but it seems probable that it will break up. I think that will contribute to sea level rise, which is important. And a very significant concern for ours. I think one of the biggest sources of uncertainty in the climate system itself, which I did not address here, are the ice sheets themselves. So what I've talked about is really, you can dig into ice sheets to learn about the history, but there's a whole other massive field of scientists who study the way the ice sheets themselves move and shift. And as they warm up, they slide off the landscapes into the ocean, and then they warm up and break apart. These are really large concerns in terms of the potential that sea level rise might be a lot faster than we predicted. I think temperature rise has kind of followed in some ways our expectations based on our CO2 usage and CO2 emissions, but the ice sheets themselves and the rate that they're melting and breaking apart appears to be a lot faster than we expected. So I agree that's a source of concern, just not one, unfortunately, that happens to be kind of a focal point of my own research.
Thank you. So you talked a little about this before, just when I had asked you the question about if somebody doesn't believe in climate change, like how you address it. We had a question that came in, which is a little bit similar, but a little bit different, which is the person works in fundraising for a climate nonprofit. So the person thinks about how people understand and react to information about climate change all the time. The person goes on to say, I realize as a research scientist, it isn't your job to translate this information in a way that's easily digestible, but do you have thoughts on how to talk about climate change in a way that makes people feel both have a sense of urgency and hope?
Well, I would say, firstly, that I do think as a scientist, it is my responsibility, at least partly my responsibility, to make that information digestible. So I do want to take some responsibility for that. That I don't think it's fair to say scientists should be allowed to operate in a silo and use rhetoric and jargon that's unapproachable. So I do want to take some responsibility for that. Firstly, as far as kind of the hope versus despair argument, I mean, that's challenging. It's challenging to answer that directly. I will say, as someone who works on the problem, I think it's easier to feel hope when you're working on it, because you feel like you're part of the solution, you're working towards it. So I do think one way to develop hope is to do something, to pursue this as maybe your career, or volunteer as part of different organizations that are helping with climate change. Because I think in that sense of hope really comes from feeling like you're doing something, as opposed to just sitting there and doom scrolling. So I think in hope, that's kind of the recommendation I offer. In terms of translatable information, I mean, I think part of it is thinking about impacts that are really, I talked a lot about global impacts, which can be sort of abstract, but thinking about local impacts. So things like, mosquitoes and rats and flooding in your basement and things like that are really part of a changing climate and maybe more prevalent in a changing climate. And so I think making sure to not just think about the big picture stuff, but really think about how a changing climate has local impacts, in my opinion, probably will have the highest likelihood of success in terms of people being involved or wanting to be involved.
And seeing the direct impact on their environment that's in front of them. Yeah, that makes a whole lot of sense. I'm just checking to see if there's any other questions. I think there's just really one last question that has come in, which is if you had one thing that you want people to take away from today, and you might have just touched upon it, what would be that one thing that as people think about climate change or talk about it or think about their own environments and what they can do? I don't know if there's that magic bullet, but I'm sort of asking for it.
Yeah, I mean, I would say the one thing, like going back to the talk, is really remembering that the climate is, our climate system is very dynamic, and I think it's part of a complacency can come from a sense that the climate system is this sort of big static feature that kind of changes a little here or there, but for the most part will kind of remain recognizable. And I would just like to counter that by saying the climate system is capable of being very unrecognizable to what we're used to. That is not a very abstract idea at all. It can be extremely unrecognizable. And so I think in terms of decision making, we need to remember that we're not really talking necessarily about little nuanced things that might happen. We're talking about fairly dramatic changes that are certainly plausible. And I think that needs to be continually part of the conversation, and need to be remembered by those who are decision makers.
Thank you. And you certainly got me when you showed us the map of us Illinois summer becoming like Texas summers, because I don't want that. But I mean, it's really dramatic impact and just what that could look like. And so thank you so much, Dr. Berkelhammer, for this wonderful presentation and discussion, and for sharing all your wonderful knowledge with us. We're certainly so proud you're on faculty at UIC and appreciate all of your time today and always. Just quickly to close us out, please just join us for our next Alumni Exchange program, which will be on next Wednesday, January 19th at noon Central Standard Time, as we will be joined by alumnus and faculty member Brian Porter. Brian will take us through a jam-packed hour talking about project management. He will walk us through the pieces of the process of project management and discuss important roles that you can implement in some of these strategies as he presents applying project management in work and life. To find a recording of this episode and any of our past episodes, please go to go.uic.edu/alumni-exchange. And of course, please be on the lookout for that brief survey I mentioned at the beginning. Thank you again for this wonderful presentation. Thank you to all of you for joining us, and we look forward to seeing you at a future Alumni Exchange program. Happy New Year, and have a great rest of your day. Thanks so much.